How might Newton interpret gravity? Is it sufficient to permit us to fly from the Earth to the moon? At any point, you might find yourself getting lost in the hands of time. It's contemplating whether how we might interpret it is simply the tip of the transient iceberg. On its head, his discovery is more than just a hypothesis. The key could lead to the secrets, revealing a universe more unpredictable and inspiring than we ever thought about envisioning. How does Brian Cox's new hypothesis challenge our conventional understanding of time, and what are the potential implications for our perception of reality? Join us on a fascinating investigation through the archives. From the beginning of time, as we move into the recently discovered body of Brian Cox's amazing theory regarding the nature of time and the vast cosmos that surrounds us. There are secrets that need to be exposed. Some of these secrets involve things related to time and gravity, fundamental parts of our reality. Imagine a world where time acts oddly, can either accelerate or slow down. The force that holds us in place might not be what it seems, but this is the realm of Albert Einstein's theories of relativity. Or how we interpret time and gravity veers off in unexpected directions, Albert Einstein, a notable name, gave us a better way of looking at the universe through his theories of relativity. His work laid the groundwork for comprehending the behavior of time under various circumstances, particularly when traveling at incredibly high speeds. It all started in the early 20th century when Albert Einstein introduced two groundbreaking theories: special relativity and general relativity. The theory of special relativity, published in 1905, altered how we see the world. In its simplest terms, it tells us that the laws of physics remain the same for all observers who aren't accelerating, regardless of their motion. This theory introduces the potential for relativistic effects, such as the well-known idea that time can expand or slow down in certain situations. One captivating thought experiment uses light to explain time dilation. Picture yourself in a spaceship moving extremely quickly, almost at the speed of light. Inside the spaceship, a light beam is moving back and forth between two mirrors that are perpendicular to the direction of motion. According to physics, the speed of light is constant for all observers, so the light beam must appear to be moving diagonally. Now, here's the interesting part. The time it takes for the light beam to travel. Its course ought to be identical for both the observer inside the spaceship and the one outside. Despite the fact that the path for the outside observer is longer, it appears as if it would take more time for the light to finish its journey. This apparent time difference between the two observers Einstein referred to as time dilation, the slowing down of time for the observer moving in relation to a stationary observer. Therefore, in this circumstance, time behaves in different ways based on your motion. Understanding how things change when they move fast, it's known as relativistic effects, is more than just a theoretical idea. Scientists use massive machines called particle accelerators, such as the Large Hadron Collider, to produce particles that travel nearly as fast as light. When things move this fast, we need to think about time in a different approach to accurately predict Albert's measurements. Einstein came up with the special theory of relativity in 1905, and it changed how the universe is especially clear to us when this theory is put into motion and time challenges our conventional assumptions. It says that the laws of physics are the same for everyone, whether they're moving or not. This is different from our everyday experience that allows us to think that something already has a tendency to move, and as we increase speed, it simply accelerates. But Einstein's theory says there's a maximum speed that nothing can exceed, the speed of light. From this perspective, events that seem to happen simultaneously for us may not appear that way for people who are moving near the speed of light. An additional result of this fresh perspective is length contraction, which indicates that if an object is advancing, it appears to be shorter in the direction it is traveling, as seen from a place that isn't moving. There is also the well-known equation E equals mc that follows right out of the special theory of relativity. It shows that energy and mass can be transformed into each other, which is a big deal for comprehending how small particles behave when they're zooming around at super-fast speeds, and also for things like the process by which particles split. In actual nuclear reactions, special relativity is more than just an abstract theory. It's a tool we employ in everyday technology, such as GPS. Your device receives signals from satellites, and because they are moving, time moves a little differently for them. If we didn't take into account this effect of time dilation in our GPS-based navigational calculations, they would be inaccurate. So, special relativity assures us that time is not the same everywhere and for everything. It depends on how things are moving. This idea challenges conventional wisdom. Compared to the truth, it's like saying our normal understanding of the universe is a little off. In comparison to the special theory of relativity, time varies. It's influenced by motion, some key ideas like the speed of light that never changes and how energy and mass are related have been proven by countless experiments. But there's more. Enter Albert Einstein's general theory of relativity. This theory, dating back to 1915, delves deeper into the relationship between gravity and the universe's structure. It overturns the outdated notion that gravity is merely a force that pulls things from a distance. Instead, it informs us that gravity takes place because space-time itself is curved or bent. It's like saying, hey, gravity isn't some mysterious force. It's just how objects move naturally. Based on Brian Cox's perception, think about general relativity as the universe as a thing with 4 dimensions. Combining 3 dimensions of space with 1 of time. In this framework, massive things like stars, planets, and even the United States influence how space-time is shaped around us. Imagine space-time like a big, stretchy blanket. When something heavy like Earth is placed on it, it makes a dent. If you place something smaller nearby, such as a ball, it will roll toward the hole. This is similar to how things behave because gravity is not a mysterious force, but a response to the bending of space-time. It's like Earth cuts a small hole in the cloak of space-time, and things move according to that dip. General relativity solidly explains how things move through the solar system, like how planets orbit the sun. It is accurate to describe the routes these planets take for us, including the manner in which they follow an elliptical course around the sun. According to Brian Cox, this is different from the old idea of gravity simply bringing things to light that are hard to explain how. Planets behave in this new way. The idea is that time and space are curving like a flexible fabric that fits better with what we see. An important moment that proved the general relativity theory was correct occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to see how light from distant stars bent as it got close to the sun. As per the idea that the vast mass of the sun would cause the starlight to slightly sway. During the eclipse, the observations exactly matched Einstein's predictions, proving the legitimacy of the theory. Just like motion can change how we experience time in special relativity, gravity also affects time. Where there is a lot of gravity, time moves at a slower rate than in regions with weaker gravity. So, if you were standing close to an enormous object like a black hole, your clock would tick more slowly than one that is far from the strong mass. General relativity introduces black holes, which are places where the gravitational force is so strong that nothing, not even light, can escape from it. The boundary area around a black hole is called the event horizon, which is similar to a point of no return. Once something reaches this boundary, it is dragged into the black hole with no way to get out. Einstein's general theory of relativity has huge implications for how the universe is initially structured. I added something called a cosmological constant to his equations because he thought the universe was static. But we discovered that the universe is getting bigger. He called this a huge error. The concept of an expanding universe is in accordance with one important part of the theory of relativity, explaining how the universe originated. The beginning of yet another significant concept derived from general relativity is gravitational waves. These are similar to ripples in space-time's fabric. It's caused by really massive objects moving fast, like when black holes or neutron stars collide. In 2015, researchers working at the Laser Interferometer Gravitational Wave Observatory LIGO directly detected gravitational waves, demonstrating a different aspect of Einstein's theory. Scientists have, over time, carried out a number of tests to determine if every theory of general relativity is correct. Time and again, it has proven to be accurate, whether it's seeing how planets move, detecting, or bending starlight. theory of gravitational waves has always been backed up by evidence. Despite the fact that gravity being completely wrong may surprise, especially considering every day we all encounter gravity, it's common in the physics world to ponder and investigate various concepts. Brian and other scientists frequently challenge established theories. And with gravity, some people question the conventional way we think about this fundamental force. One theory, modified Newtonian dynamics (MOND), suggests that at low speeds, gravity behaves differently, especially in universes without needing dark matter. Instead of adding invisible matter, MOND suggests that gravity becomes stronger at low velocities. The gravity debate also includes dark matter and the mysterious energy introduced to explain certain critics of space phenomena. They argue that these might not be needed, and alternative ideas can explain what we observe. Some researchers who disagree with Einstein's gravity theory explore other possibilities, like theories involving unidentified forces or particles that have the potential to alter or enhance our understanding. It's important to be aware that in science, innovative concepts are not overlooked. They're carefully tested to see if they make sense, like the idea of Einstein's four-dimensional space-time, where time travel into the past may be limited by the light of day. This has been imaginatively investigated alongside concepts like wormholes and shortcuts. Stephen Hawking's conjecture about chronology protection proposes that one could travel back in time, but physics-wise, it seems unlikely, taking into account ongoing tests and observations. We determine whether these novel theories can talk about things like how strong gravity is in a manner similar to what we already know. But different ideas, none of which have successfully replaced the gravity. Laws that have been around for a long time, questioning and challenging ideas are vital parts of how science learns. New things that call for more investigation and a better understanding of the universe. In the world of gravity theories, general relativity remains the most important and effective one. Despite obstacles and alternative strategies, it consistently passes tests with flying colors and explains various phenomena, like how planets move and how light bends around massive objects. General relativity stands strong because it's simple and covers a wide variety of phenomena. As we previously discussed, Einstein's special theory of relativity suggests that time can act in different ways depending on how fast you're moving. Let's find out exactly how. This idea has an impact on the real world, especially when it comes to space travel. It is exciting but challenging because space is vast and conforms to Einstein's theory that the speed of light is the fastest anything can go. Navigating between stars is extremely difficult, despite the use of cutting-edge technology due to the extensive time frames involved in reaching the nearest stars. Consider the famous twin paradox to comprehend what occurs over time when traveling in space. Let's say one twin stays on Earth, and the other twin travels to a distant star. When traveling through space, when the twin returns, they discover that less time has passed for them rather than their twin on Earth. This means they kind of travel into the future, which is essential for space travelers, due to the fact that the longer the journey, the more time slows down. If astronauts travel to nearby stars where there is a significant halt in time, they might age at a slower rate than Earthlings. Despite the fact that it may seem like science fiction, it's a real effect from the theory. Consider what would happen if humans sent a crew to a star system not too far away. Because it's such a vast distance, the journey might take many years, even if they travel fast. For the astronauts on the spacecraft, time would appear to be slower because of time dilation. Meanwhile, on Earth, much more time would have passed. Time dilation not only affects living things, but also has an impact on technology. Systems for communication and computers on spacecraft need to account for time dilation to guarantee precision and functioning. Space exploration difficulties at high speeds include physical aspects, such as prolonged isolation and exposure to cosmic radiation, and psychological effects of being away from Earth for a significant portion of our daily lives. We can see how time dilation affects GPS, or the Global Positioning System, which depends on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it's crucial to account for these consequences in GPS calculations. Failing to do so would have a significant impact on the accuracy of navigation systems. Now, Let's examine the reasons why time moves in one direction. Time governs our lives, moving from the past to the present and into the future. The fundamental aspect of time is its one-way flow to our existence. But why does time have this one-way nature? To comprehend this, let's examine the concept of entropy, which measures disorder or randomness in a system. Entropy is tied to the arrow of time, and it tends to rise over time, which results in the second law of thermodynamics. This law expresses this relationship, stating that in any isolated system, total entropy will either go up or at best stay constant. Entropy tends to increase naturally, but does not decrease on its own. Understanding how things get more disordered around us enables us to observe the linear progression of time. Imagine a deck of cards neatly organized. If we shuffle them, they become chaotic and haphazard. This transition from order to disorder shows how time moves in one direction, as seen in everyday phenomena like ice melting or a stirred coffee cup getting messy. This progression of time works differently at various levels. If we look at tiny particles, the laws of physics allow things that can move forward and backward in time, or the concept of time reversal symmetry. The discrepancy between this and the irreversible changes we see in the everyday world is the source of something called initial conditions. The large, complex world we live in is the result of many particles and how they interact. It's making a time arrow that only goes one way. This notion that time moves in a single direction is more than just mundane. It's equally valid across the entire cosmic universe. The universe has been progressing in one direction since the Big Bang. The universe began in a state of low entropy and has evolved into more chaotic galaxies over billions of years. Scientists continue to attempt to determine why the universe began in such a well-ordered state. Even in the smallest universe governed by quantum mechanics, which deals with tiny particles, there's a time arrow indicating how particles evolve over time. It appears uniform, but when we look at them, things can no longer be changed. Brian believes that it's not just a physics thing. Our brains also experience time in one direction. Think back to the past, embrace the present, and think about the future in a sequence. This mental arrow of time is tied to how we perceive the external world's arrow of time. This concept of time has significant logical ramifications that examine how we understand reality. Time is a crucial component of our life experiences and how we grasp the world. Without this one-way progression in time, everything would look very different. Implications for our actions, cause and effect, wouldn't make sense.